Right now, across the globe, state-sponsored actors are actively deploying frontier AI models to orchestrate advanced, offensive cyber espionage campaigns. To understand the capability of these models, the cybersecurity industry typically measures AI hacking skills using Capture the Flag, or CTF, challenges, isolated single-step puzzles. This chart tracks model performance on cyber evaluation since 2022. Frontier models are rapidly saturating these isolated benchmarks, but sterile puzzle environments create a false sense of security, failing to test an agent's ability to maintain context over a long-horizon operation. To measure actual offensive capability, researchers at the UK AI Security Institute abandoned CTFs entirely. They evaluated 7 recent models on bespoke, multi-step simulated enterprise networks. The results isolate 2 distinct axes of capability growth: the generational leaps between new model architectures and the scaling of raw inference time compute. This shift in testing reveals that simply increasing the token budget to 100 million can change the depth of an agent's reach into a network. Instead of looking at static intelligence scores, we have to evaluate what happens when you supply the reasoning cycle with massive token budgets to find the actual ceiling of the agent's autonomous performance. Researchers built the last ones, a virtualized corporate network attack chain of 32 steps across 9 milestones. Starting blind, the agent must breach the VPN, move laterally through the Charlie and Oscar subnets, and reach the Alpha local subnet to exfiltrate a sensitive database. The simulation features production software and common enterprise misconfigurations. Crucially, there are no active defenders or detection penalties to stop the agent if it makes a mistake. The paper also evaluates a secondary environment called Cooling Tower, a 7-step industrial control system range designed to simulate physical disruption at a power plant. Based on the complexity and interdependence of the steps, completing the last ones would require approximately 14 hours of continuous effort from an expert human penetration tester. The models were equipped with a standard Kali Linux environment and operated using a reason and act loop. They had 0 specialized scaffolding or tailored hacking tools. This minimal setup isolates the underlying model's capability. Every pivot, exploit, and discovered credential is the direct result of the AI's autonomous reasoning, proving the success comes from the machine, not human engineering tricks. This plot highlights hollow circles representing a 10 million token budget. In August 2024, GPT-4o stalls out at an average of just 1.7 steps, failing to breach the first internal subnet. But 18 months later, Opus 4.6 jumps to a 9.8-step average completion rate. Translating that data into action, at 9.8 steps, the model is autonomously breaching the VPN, moving laterally via ASREP roasting, extracting saved browser credentials, and setting up command infrastructure. Newer generations extract more utility per token. They execute commands with higher efficiency and apply deeper specialist knowledge than their predecessors. The next question is, what happens to the agent's penetration depth if we lift the 10 million token constraint entirely? Long-horizon tasks pose a mechanical challenge. As an agent executes dozens of terminal commands and reads massive log files, it quickly exhausts its context window space. To solve this, researchers use context compaction. When the window reaches 80% capacity, the model summarizes its task-relevant history, its discoveries, network topology, and credentials, and injects that summary into a fresh context window to continue hacking. This logarithmic chart graphs completed steps against cumulative tokens. Notice Opus 4.6's steep red trajectory. Scaling the budget to 100 million tokens yields a 59% deeper penetration rate. In its peak run, it successfully navigated 22 of 32 steps, showing no sign of plateauing. To achieve that level of access from a standing start, an expert human penetration tester would require roughly 6 hours of continuous, focused work. Because of input token caching and falling inference costs, this entire 100 million token run cost approximately $80 in API fees. For those $80, the agent spent 10 hours of wall clock time relentlessly probing the network, without needing sleep, breaks, or shift changes. Compute scaling requires 0 technical sophistication from the threat actor. Deeper network penetration is now a direct function of purchasing a larger token budget. But if compute scales log linearly, we have to ask why no model successfully exfiltrated the Alpha local database at the end of the range. This heat map shows completion rates at 100 million tokens. The stark drop-offs are capability walls. The first bottleneck requires real-time NTLM relay attacks, breaking the sequential reason and act loop. A second wall at milestones 7 and 8 shows agents lack specialized knowledge to compromise CI/CD supply chains. However, the evaluation of the cooling tower industrial control system revealed an anomaly in how these models solve problems when they hit a wall. They completely bypassed the intended web exploitation path, analyzing raw network traffic to autonomously deduce the proprietary protocols running on the programmable logic controllers. In some instances, the agents utilized an unintended fuzzing technique, brute forcing session identifiers to bypass authentication entirely, even though the transcript showed the model did not actually understand the mechanism it had just exploited. Models fail on complex, human-designed exploit chains, but their alien approach to problem-solving creates highly unpredictable success vectors that human defenders simply will not anticipate. When we place saturated performance rates on isolated CTF challenges next to hard stops inside a real network topology, the actual threat profile becomes clear. Zero-click, fully autonomous enterprise network takeovers are not yet a reality. Agents still fail when forced to execute long sequences involving specialized cryptography or custom malware development. But the barrier to entry for the first 60% of an enterprise intrusion is rapidly collapsing. The immediate operational threat is human-AI teaming. A mid-tier human operator can deploy an $80 token budget to autonomously map a network, move laterally, and escalate privileges. The human only needs to step in manually to solve high-complexity bottlenecks that stump the machine. Enterprise security posture must adapt immediately. We are facing a landscape where adversarial reconnaissance and initial access scale at the exact speed of inference compute, breaking the assumption that large-scale network intrusions require a massive team of human attackers.